In this tutorial, we will be discussing how to make a buffer. So let's try to figure out what the pH would be for a buffer system. What is the pH of sodium carbonate and sodium bicarbonate buffer solution when 8.4 grams of sodium bicarbonate and 16 grams of sodium carbonate are mixed together in a 1 liter volumetric flask? The Ka for bicarbonate is 5.6 times 10 to the negative 11. So, in order to figure this out, the first thing we need to do is figure out the molarity of the solutions. To do that, we first need to know what the moles are. So I have 8.4 grams of sodium bicarbonate. The molar mass of this is 84. I figured that out by looking on the periodic table. I added up all the elements. So 8.4 divided by 84 is 0.10 moles. To figure out the molarity, I would then divide that by 1 liter. That's because it's in 1 liter flask. Okay, so let's look at the sodium the sodium carbonate now. 16 grams the molar mass of this is 106. And that comes out to be 0.15. Once again, we need to figure out the actual concentration of this. So that's 0.15 moles per 1 liter. Because once again, it's in a 1 liter volumetric flask. That comes out to be 0.15 molar. Alright, so we're going to actually try to use the Henderson-Hasselbalch equation for this, because you'll notice that we have the concentrations, and those concentrations are much, much bigger than the Ka. So that equation is pH is equal to the pKa plus the log of the conjugate base over the acid concentrations. Okay, from here, I'm looking for the pH. pKa would be the negative log of the Ka, which we know from the previous slide, right up here, is 5.6 times 10 to the negative 11. Plus the log of the concentrations of the conjugate base and the acid, which is 0.15 and 0.10. So the pH is then equal to 10.25 plus the log of 0.15 divided by 0.1, which is 1.5. Which comes out to be 0.176. Add those together, and it comes out to be 10.43. You would actually expect it to be on the basic side because of the fact that we have more of the base than we do the acid. Alright, so you want a buffer that has a pH of 4.30. Given the following possibilities, select the combination that would meet this criterion. So, when you're looking at buffers, you want a buffer with a pKa plus or minus 1. So that means we're looking for anything with a pKa of 3.30 to 5.30. You're looking for that range. So what I'm going to do is I'm going to take the negative log of each of these. Negative log of each Ka. So the first one, 1.2 times 10 to the negative 2, when I take the negative log of that, I get 1.92. The second one, when I take the negative log, I get 4.74. And the third one, when I take the negative log, it comes out to be 9.40. As a result, the acetic acid and acetate are the most likely pair. Alright, so here's another problem. You need to make a 1 liter buffer solution having a pH of 4.30 from that acetic acid and sodium acetate. What concentrations of those chemicals will you need to prepare? And you need the Ka of 1.8 times 10 to the negative 5. I'm going to go about doing this using the Hasselbalch equation again. There's a couple different ways to go about doing it, and both ways will give you the same answer. If you want, you can use this way. That's where you take 10 to the x of 4.3, divide it by the Ka, and then that'll give you your ratio. I'm going to do it using the Henderson-Hasselbalch equation since that's what we used on the previous question. So pH is equal to the negative log of the Ka plus the log of the base, which is the acetate, over the concentration of the acetic acid, the acid. So pH we know is a 4.30, negative log of 1.8 times 10 to the negative 5 plus the log of this ratio. So that's 4.30. The negative log of 1.8 times 10 to the negative 5 comes out to be 4.74 plus the log of the acid and the base concentrations. So that comes out to be negative 0.44 the base over the acid. So first thing I'm going to do now is I'm going to take 10 to the x, or the inverse log of the negative 0.44. That comes out to be, so I'm going to do 10 to the x here, which then cancels the log and the 10 to x out on the right. 0.363 the concentration of the base over the concentration of the acid. So that is going to be a ratio. So for every 1 molar of the base, of the acid HOAC, we're going to need 0.363 molar of the base. Every 1 molar, that would be the ratio, every 1 molar of the acetic acid, we would need 0.363 molar of the sodium acetate. Alright, let's do another one. This will be our last one. How many grams of sodium hydrogen phosphate must be added to 250 milliliters of 0.25 molar sodium H2PO4 to make the buffer a 7.0 pH? We have the Ka right here. So the pH, once again, is equal to the pKa plus the log of the base over the acid. We know we're trying to get a pH of 7. The pKa would be the negative log of 6.17 times 10 to the negative 8 plus the log of the base over the acid, which they tell us the acid is 0.25. So we're really just looking for the base at the final end. So 7.0 is equal to, if I put negative log of 6.17 times 10 to the negative 8 into my calculator, I come up with 7.21 plus the log of all this. So that comes out to be negative 0.21 is equal to the log of the x, our base, over 0.25. Let's rewrite this on the next page. Alright, so to get rid of that log, I want to take 10 to the x of both sides. That cancels out the log on the right hand side. So that leaves us with the base over 0.25. 10 to the x of negative 0.25 comes out to be 0.154. I'm sorry, that comes out to be I skipped a step, 0.617. Cross multiply. So that gives us a base. Once I do 0.617 times 0.25, that's going to equal 0.154 molar. That's where I got the 0.154 from. Alright, so we want to know how many grams. So in order to get to grams, we have to figure out how many moles we need. We have 250 milliliters. Therefore, 0.154 is equal to x over 0.25 liters. Cross multiply to get how many moles there are. 0.385 moles. Now from here I use the molar mass to get to grams. 1 mole is 142 grams. Multiply that out and it comes out to be 5.47 grams. And that's how you solve for buffer equations.